All right. So we are on our last section. Okay? On our last section of chapter 2. This will be the last stuff that'll be on test 1. We basically have a test per chapter. We made it through this last stuff a little bit faster than I thought we would. I had already announced that test 1 would be on next Wednesday, around on the 9th. So we'll leave it there. But what that means is we'll be done with 2.8 today. What that means is we'll have 2 class periods before the test. So on Friday, let's just do a WebAssign day. Okay, if you're completely caught up on everything in WebAssign, then you don't have to come. Okay, but we'll do Friday. It'll be kind of like just study group. Okay, I'll be glad to help with any WebAssign problems that you have and work on Friday. And if you need an extension on something, you have one that you didn't do that you need to go back and do or something like that, you can request an extension and I'll open that up. We can do that Friday. We'll just take that opportunity to get all caught up and get any help we need on Friday. And then Monday, I just posted a practice test in WebAssign. So on Monday, we'll go through and we'll work any problems you want to work from that assignment. That assignment is 0 points, the practice test. So if you see one, you're like, oh, that one's easy, I don't even want to mess with it, that's fine. You can do as much or as little of it as you want to. It's just up to you. It's just a study tool. Okay. A lot of them are repeats from problems we had in the assignments. So if you're comfortable with it, don't worry about it, but it's a good study tool. Thoughts or questions on that schedule? You can, yeah. If you have a particular problem you're stuck on, yeah, you can do that. That way I can see which problem you're looking at. Yeah, probably because it'll send me an email when you click on that. Probably that's a little easier because it takes me straight to that problem and I can see what you're looking at a little easier. Anything else? Do we have problems we need to work? Got one? Number 5 on 2.5. Okay. Let's take a look. If the Wi-Fi will cooperate. Come on, come on. And Mavs need to sign it. That might be it. Okay. Yep. Did you? Oh boy. Well. Let me try disconnecting from the Wi-Fi and reconnecting to that. Yeah, I think that did help. All right, let's see. Which one's number 5? Whoop, whoop, whoop. Oh, okay. Number 5, let's see if I can zoom in some more here. It's the one that gives us this question, how would we remove a discontinuity? And so we're trying to think about how could we redefine things so that we will not have a discontinuity, in this case at 2. So on this one, the reason why we have a discontinuity at 2 is because if we try to evaluate our function at 2, we'll get 0 in the denominator. And so it's undefined there. And if you think about the graph, that would mean we have the graph of this thing and we have a hole at x equals 2. So really, if you go back to our 3 properties we have to have for continuity, it's failing on the last one. Well, it's failing that it's undefined at x equals 2 as well. It's also failing at the last one that our limit at 2 does not equal the functional value at 2. So if we can figure out a function value to give this thing so it matches the limit, then we'll be in good shape. And that's a big mouthful to talk about. It's not a really bad problem. And because what we need to do is we need to find the limit here as we approach 2. And once we figure that number out, we can define our function to equal that number, and then we'll be good, we'll be continuous. So we've done several like this as far as finding the limit. And so we want the limit of this thing. Limit as x approaches 2. It was something over x minus 2. What was it? X squared minus x minus 2. So if we can find this limit, then we'll define our function to equal whatever this limit is at 2, and then we'll be continuous. Okay, so direct substitution is obviously not going to work. Right? That's our whole problem. So what can we do? Yeah, we can try to factor. So if we factor the numerator here, we need factors of -2. That'll give us -1, -2, and +1. And on the bottom we have x minus 2. So what we want happens, we get a cancellation in the denominator. So what's our limit going to be? We just direct substitute now. Yeah, 3. So since the limit as x approaches 2 would be 3, what we want to do to make sure it's continuous is we want f of 2 to equal 3. We want these two things to be the same. So maybe a little confusing on the wording of the problem, but we just want to make sure that the limit of our function as x approaches 2 is the same thing we get when we plug 2 into our function. Does that help? Anybody have any other ones? 7 off that same assignment? If I can get my screen to cooperate. Okay, so 7 is probably more straightforward than it looks. So the idea here says use continuity to evaluate the limit. That's the big hint. So the idea is that if we have a product, right, we have x times the square root of 41 minus x squared. We have a product, and if we look at each individual piece, so the thing underneath the radical is just a polynomial, so that's continuous. We had a property that if we take a root of a continuous function is continuous, and then we had a property that said if we multiply continuous functions together, so x by itself would just be another polynomial. So we would have a polynomial times another continuous function, so it'd be continuous. So on that one, it's just direct substitution. So it looks weird, but it's just direct substitution. So let's see on mine. what would we get? $41. We can just do direct substitution because every piece is continuous, so the whole thing's got to be continuous. 41 minus 25, 60. And 5 times 4, we should get. That's all. And then I think 8. 8 is a similar type of deal. It looks really complicated potentially. But sine is continuous. X is a polynomial, so it's continuous. The sum of two continuous functions is continuous. If we take a function that is continuous and plug it into another function, we get continuity. And so really all we end up having to do is just plug in pi. That one. Not as complicated as it looks because of the continuity. Continuity makes our life easier there. May I have other ones? Yep. 6. Oh, the domain. So we just want the domain of the function. Huh? Okay. So polynomials are defined everywhere. With a rational function, the thing we have to look out for with the domain is the x values that make the denominator 0 would not be in the domain, and so we would have to leave those out. But on this one, so we're focusing on the x squared plus 9 part. We want to know if that's going to cause us any trouble. We've got something over x squared plus 9. So is there any real number that would make x squared plus 9 0? No. If you set it equal to, so you could set it equal to 0 and solve. But if you do, we'll be taking the square root of -9. We'll get complex answers in there. There's not a real number that would make the denominator 0. So on this one, we don't have anything to worry about with our domain. It's just going to be all real numbers again, so it'll be negative. Positive. Now yeah, go ahead. Yeah, so then if we had some value we needed to leave out, so like if we had we figured out that x can't be 3, then our domain, the way we would write it in interval notation is it would be -infinity to 3 with the parenthesis because we're leaving 3 out, and then we would pick back up right after 3 and go to infinity, and then we'd have to put the two pieces together with the unit. That's kind of ugly. If you leave a number out, you've got a hole there in the number line. Looks like that. And then just while we're reviewing domain, if we had something like we figured out our x values had to be like greater than or equal to 4, right? Maybe we had an expression underneath the square root, and we can't let it be negative. Then the way we would write that domain in interval notation is we think about the smallest value we could have. In this case, it's 4, and we want to include it because we have the equal sign. And then it could be bigger than that, so we could go to little interval notation refresher. Other questions? Good stuff. That's a good use of class time. Well, I'll look at it. Let's see. define if we have a discontinuity. So the ways we have discontinuities, we can have a hole in the graph, so if it's undefined, we have discontinuity. Or we could have a jump, where we have a hole coming from one direction and it's defined coming from the other direction. Or we could have a vertical asymptote. So here the main things we're having to look at is we're looking at like where the pieces of the graph meet up. So like at 0, we would get 6 from this piece. And then coming from the other side, if we plug 0 into e to the x, we would get 1, anything to the 0th power. So those are not going to match. So for sure, we got a discontinuity at 0. Here we could look at the behavior around 1. So if we put in 1 here, we would get 3. And if we put 1 in there, we're going to get e. So they're not going to match. So we got a discontinuity there. And then as far as the continuous from the left or from the right parts, we just look at where it's defined. So between these two pieces, it's going to be defined 0 on this part. And so if we're thinking about the junction here, we got x plus 6 coming in, and then we start with the e. But it's defined on the e side. So coming from the right, it'll be continuous, but coming from the left, it won't be. Got the hole there. There's some help. We won't work it. That's some help. And then think about the other junction with like at x equals 1 there. And then you pick the graph. It's really not, it's not as bad as it looks. It's you later. That's okay. Anything else? Okay. All right, well, let's look at section 2.8 then. We don't really have like new calculations or anything. In 2.8, what we're doing, we're just kind of shifting our thinking a little bit. So we've been interpreting the derivative, that special limit we saw last time. Been interpreting the derivative as the slope of the tangent line at a certain point on a function. Today we're going to think about the derivative itself as a function. We can define it as a function. Okay, so we're going to think about that a little bit here. So the thing we messed with last time, right, we had this limit, number 1, and we had a couple of ways we could write it. That's one of the versions. And we said we call that limit f prime at a, or the derivative of f at the x value a. The major change we're taking here is that we're not thinking about a as being a number. Instead, in its place where we had a, we're going to let that spot be variable. Let that spot be variable. And that makes sense to do that because remember, our derivative is the slope of the tangent line at a certain point, a certain x value for a. So we can think about how that's going to change when we change x values. We can let that be variable, and we get a function. So our main goals in this section is we want to think about how this derivative function relates to the original function. So we're going to do some things like look at the graph of a function and think about what the graph of the derivative would look like. And then we'll also have a little bit of terminology that we need to pick up on. Not too terrible. So let's look at one. Okay. We have this new function we call the derivative of f. And we've already talked about like geometric interpretation if we think about the value of our derivative function at some a. Just another way of saying the same things we've talked about last time. And f prime here, our derivative, we call it that because it's been derived from taking that special limit on our function that we started with. So here's one important piece of information when we're thinking about our derivative as a function. It's domain. The domain is going to be all the x values where the derivative exists. So we might have some x values where the derivative does not exist. Maybe domain's everything else. And the domain's not necessarily the same as the domain of the function. We'll see. If we move through the semester, maybe not. We won't focus on that too much. Let's think about the graphs. So here's some generic function f. Looks like maybe some kind of polynomial or something. And we want to kind of analyze the graph of f and think about what the graph of f prime, what the graph of the derivative would look like. So one thing you can kind of start with, any special behavior you see in the graph of the function and think about how that would relate to the derivative. So things I'm thinking about is like right here, maybe it looks like it's pretty close to an x value of 1/2. What would be special about our tangent line there? So we have a negative tangent line, and then here when we get to the bottom of this valley, what happens to our tangent line? It's 0. So that's something special to look for on a graph when you have 0 values. And then our tangent line would have a positive slope, and then when we get to the top of this peak, it's 0 again. And it'll go negative, and then down here, when we get to the bottom of this valley, we'll have another 0 value for our derivative, and it'll go off positive. And so if we're thinking about what the graph of our derivative is going to look like, that's one of the things we can think about. Something else the textbook suggests is that we just pick some x value, and we can estimate what the slope of the tangent line is going to be on our original function. So here they picked 5 as the x value, and they've estimated the slope of the tangent line there is about 3/2, or about 1/2. So if that's true, then on our slope of our derivative, we should have the 0.5 and 1.5. I think I said 1/2. 1.5, 0.5, 1.5 should be there. That's tricky to do sometimes, especially if you don't have all the numbers. You don't have the grid in there where you can actually get those slopes. And again, the two big things we can focus on without having too much detail at all on our graph is we can focus on what the sine of our derivative will be, because that's the sine of the slope of the tangent line. And then we can focus on where our derivative will be 0. And that's anywhere we'll have a horizontal tangent line. So as you follow the blue graph down, right, our tangent line would be negative slope there. And then when we get to this point A, whatever that x value is, we've got to go through the x-axis because the slope of our tangent line is 0, so that means the functional value of our derivative should be 0. And then if you follow from there to B, we've got positive slope, so our graph should be above the x-axis, be positive territory. Then again, when we get to this number B, we have a horizontal tangent line, so we've got to at least touch the x-axis again. There we'll have negative slope, so we're down below the x-axis. We hit 0 again at C where we had that horizontal tangent line. And then for the rest of it, we've got a positive slope. And it looks like it's getting bigger, getting steeper as we go. So our graph's positive and it's increasing. This takes some practice. Thinking about, based on the graph of the function, what's the graph of the derivative going to look like? It's almost like adding a dimension to things. Have to take some time and think your way through it. Again, those 0 derivatives are really good places to think about. And then thinking about the sign, is my graph of my derivative going to be above or below the x-axis? You can think about those two things, then you get a long way toward figuring out what the graph of the derivative will look like. So do you see what we're doing? We're tracking, like if we start at the beginning of the blue line and track the value of our tangent line, the slope of the tangent line, as we move across the blue graph, those values, here are our points on the derivative. Can be a little tricky to wrap your head around. Let's look at thinking our way through another one here. Thinking about this function. Yeah, you're good. Okay, so let's think about square root of x as our function. If you, right now the only way we have is to take the definition of a derivative. We'd have to find the limit, that difference quotient thing, to get our derivative, but just go with it for right now. Okay, here's our derivative. So if the function is square root of x, our derivative would be 1 over 2 square root of x. And if you look at the two graphs, you can match up the behavior that's going on. So here, we think about our tangent line coming in close to 0, not quite at 0, but if you think about coming in close to 0, we're going to have a really steep tangent line, right, with a positive slope. So we're going to have really big positive values when we're close to 0. And then as our graph moves to the right, our tangent line slope is going to get smaller and smaller, and it's going to get closer to 0, not quite 0, because this thing's not going to go completely horizontal, but our slope's going to get smaller and smaller, and that's what happens with our derivative. Like we have some asymptotic behavior here at the x-axis. So large positive slope close to 0. That's a large positive values here. And then small positive slope close to 0 as we go toward infinity. So trying to relate those two graphs to questions on that one or the graph before? Kind of what we're focusing in on looking at. Okay. So these really just take some practice. So that's what some of the problems in the homework assignment are. Okay, it'll give you a graph of a function and ask you to match it up with a graph of the derivative. So one more time, focus on places where the derivative will be 0, where we have a horizontal tangent line, and match those up. And then you can track the sign, not positive or negative slope. Things we can look at to give us an idea. Okay. Order of business number 2 in this section is to talk about some of the bajillion different notations that it used for derivative. Okay. So we have focused on f prime of x, the derivative of our function at x. All of these notations mean the same thing. So if instead we were calling our function, instead of calling it a function, if we were saying y equals something, then we could talk about y prime or the derivative of y, that y with a tick mark. Okay. The next three are all related. Okay. If we're defining our function as y equals something, then we could say dy dx. Or if we're calling our function f, we could say df dx. Or we could just say d dx, whatever our function is. Those all mean the derivative. And then we got two more. We've got a capital D f of x and a capital D subscript x f of x. All of those can be used to represent finding the derivative of whatever function we're looking at. The capital D notation or the d dx notation get called the differential operators because they are we're finding the derivative, so we call that process differentiation, which is a mouthful. Differentiation, kind of a hard word to enunciate. So, kind of sad, and this is really not even all the notation. Sometimes in physics settings for the derivative, they'll use dot notation, so they'll have like y dot for the derivative instead of a tick mark. And so everybody kind of has their own spin on this thing. Part of the reason for that is historically, if you go back to the roots of when calculus was developed, it was developed for the purpose, okay, of solving physics problems. That's when we get our ties to physics, calculus class. But it was developed kind of nowadays. Everybody used to say it was Isaac Newton. Isaac Newton developed calculus, and he did. But there's also, debatably, I think now most people officially recognize that it was also developed at the same time by somebody else named Leibniz. And they both had their own notations that they used as they developed. So both of those get used, and then we've just got all of our own little spins on these notations. So sadly, we have a lot. So the dy dx notation, that one comes from Leibniz. And right now, we can just think about this dy dx as just being all one thing. And it just stands for derivative. Fine. So in that case, you could say dy dx means exactly the same thing as f prime of x. No problem. It'll be useful to us down the road to think about it actually as a ratio of two things. But right now, you don't have to. And a lot of times that dy dx gets lumped into that delta notation we used last time, and you can write things like this. Y dx equals the limit as delta x approaches 0 of delta y over delta x. That is kind of nice, I'll admit. But right now, you can just think about it as being the derivative. Okay. And if you switch to some of these other notations, you have to have some other way of writing what we've been writing. Like in the last section, we wrote f prime of a. Now we're actually using a number, and we're finding f prime at some x value on the graph. And so if you use something like dy dx, how do you write that? Well, the way that gets notated is you can have dy dx and then either just the vertical bar, or you can have like a bracket, and then down at the bottom you subscript x equals whatever number. So in that case, this dy dx with the bar and the x equals some number is the same thing as saying f prime at some number. We're just going to evaluate the derivative at some certain x value. Then we get a definition. It says we call a function differentiable at a, so differentiable at some number if the derivative exists at that number. And then if our function is differentiable for every number in an interval, we can say the function is differentiable on the interval. And oh yeah, so not the next term. So let's get away from all that notation. Let's actually think about a function. Let's think about absolute value function. It turns out, like polynomials, they're differentiable everywhere, things like that. We'll see a theorem that ties some of all that together in a second. So if we're trying to talk about functions that are not differentiable at some value, we have to get into not the standard polynomial or rational functions. So here we're looking at absolute value of x. You remember what the graph of the absolute value looks like? What kind of shape does it have? It's like a V, yeah, it's like a V. Yeah. So you've got y equals x in the quadrant 1, got that part of that graph, and then instead of it going down into quadrant 3, everything turns positive, so it flips up in a quadrant 2 and you get the V. So let's think about where this thing would be differentiable, or in other words, what x values would we be able to find a derivative for absolute value. So if we think about the positive x values, the positive side of our graph, then we can simplify things. Instead of thinking about absolute value of x, we can just think about y equals x, f of x is x. So if we think about finding the derivative, our derivative anywhere where x is bigger than 0 is going to work out to 1. So that's saying the slope of our tangent line is going to be 1 anytime we have a positive x value. And then that's true. Okay, if you think about, we said it's like the y equals x part. So that has a slope of 1. Our tangent line will have a slope of 1. Straight line, so it's a little easier. If we go over to the negative side, if we think about where we have negative x values, and the absolute value of x is going to give us negative x, and if we try to find our derivative over there, almost the same thing happens, but instead we have negative x, so we get a minus sign thrown in there. Tells us that our derivative for every x value that's smaller than 0 is going to be negative 1. And that's just that limit definition that we played with last time. Negative 1. And that makes sense, right? We have negative slope over in quadrant 2. It is negative 1. The more interesting piece to think about is what happens at 0. What happens at 0? So if we try to plug into our limit definition of derivative for 0, then this is like the f of a plus h minus f of a thing we did last time, right? But here our a is 0. So then if we simplify that down, we'll get absolute value of h minus 0, which is just absolute value of h. And then we've got h on the bottom. And with absolute value of h over h, you can't just straight up cancel that, because absolute value of h is not always the same thing as h. It depends on which side of 0 you're on. If we're on the positive side, if we're coming in from the right, yeah, then we can cancel that, because in that case, positive values, absolute values, the same thing as just h. But if we come in from the left side, then the absolute value of h would be negative, so we would get negative 1. So at 0, when we do the limit, try to find the limit, the two-sided limit, if we come in from the right, it's 1. If we come in from the left, it's negative 1. So what's that tell us about the two-sided limit? Yeah, so one way we're coming into 1, the other way we're coming into -1. So the two-sided limit does not exist, right? Because these don't match. Two-sided limit does not exist because the limit from the right and the limit from the left don't match. So what does that mean about our derivative? If we try to find the derivative, to do that we have to take this two-sided limit. But if our two-sided limit doesn't exist, what does that mean about our derivative? It's not gonna, we don't have a value for it. So our derivative function here would be undefined at x equals 0. So that would mean, as far as differentiability, that the absolute value of x is not differentiable at x equals 0. Because that limit definition of our derivative breaks down. If we think about the graph, okay, so here would be our graph of the derivative function. It's undefined at 0, so we would say our function is non-differentiable. It's not differentiable at x equals 0. So if we think about the graph, when does that happen? So there's absolute value of x. Everywhere over here, our tangent line looks just like the graph. We've got a positive tangent line with a slope of 1. Everywhere on the negative side, our tangent line looks just like the graph. We have a negative slope tangent line with a slope of -1. But then at 0, we've got this corner. So what's our tangent line at 0? That's the problem. That's the problem base. So you could think maybe, okay, there's my tangent line geometrically. Nice tangent at 0. Or you could think maybe at 0, this is my tangent line. Or this could be a tangent line at x equals 0. So we've got really an infinite number of choices for lines that we could call tangent lines, starting here and then rotating all the way through infinite number of angles until you get back here. So we don't have one tangent line at x equals 0 because of that corner, and because of that corner. So having a corner on the graph like that, okay, if it was curved, if it was rounded off, we would be fine. But because of that corner, at the x value where the corner occurs, our derivative does not exist, so our function is not differentiable. So that's one of a few things that can cause a function to not be differentiable. So before we look at the other ones, let's get this last theorem out of the way. One more theorem. This one says if f is differentiable at some number, then f is continuous at some number, guaranteed. So if we know a function is differentiable, some x value or on some interval, then it's also continuous at those places. If we try to take the converse of that, if we try to switch the order, our statement's not true anymore. It is not true that just because f is continuous, it means it's differentiable. That's not true. But if you know it's differentiable, you do know it's continuous. So like here, if we've got a group of functions, we'll take a box and put all the functions in there. Then we've got a little compartment over here that we'll call continuous functions. Because there are functions that are not continuous, right? We've seen that. We can have discontinuities. And then inside the continuous bubble, we've got differentiable. That's like a subset of continuity. So what are the things that make differentiability break down? Okay, we've seen one. Um, we've seen if we have a corner, then definitely we've got some point where our function is not differentiable. So the textbook calls it having a corner or a kink in our function. Not be differentiable at the corner. And it's differentiable everywhere else. Everywhere else is just a straight line. And so that's one thing. Another thing that could cause a problem is if we have a vertical tangent line. If we have a vertical tangent line, then the slope of our tangent line is approaching infinity. So we'll have an infinite limit. If we have a limit, we'll have an infinite limit. So then we won't be able to get a value out for our derivative because we can't have a value of infinity as our slope. And two other things. So, well, really, they're breaking this down into one case. Typically, you'll hear this called two different cases. So let's talk about this one first. The case where we have a vertical tangent line. So here we've got some blue curve, and we have a really steep slope as we get close to this a value, and then at one particular point the tangent line pops completely vertical, and then it goes back down as we move away from there. So we're not failing the vertical line test with our blue line. It just so happens that we've got one point in here that our tangent line is completely vertical. Goes through that one point. So if we have a vertical tangent line, what's the slope of a vertical line? Horizontal line has slope 0. Vertical line has a slope of what? Well, that's a good thing. Yeah, what do we call it? We call it undefined. Undefined slope. Undefined. So if the slope of our tangent line is undefined, then we're not differentiable there. We can't find the derivative. The vertical tangent line comes into play. This other one, okay, there's a bunch of tangent lines drawn in there, so it makes it look kind of strange. So without all the tangent lines drawn in there, we're looking at something like, I can draw it better. So we have more of a point, like a sharp point. That kind of behavior, usually you'll see it called a cusp. So in that case, you can think about it either like they're illustrating here, where you have a vertical tangent line right at the point, or you could think about like just thinking about trying to draw a tangent line in there. We've got infinitely many lines we could draw in that only touch the point at one place, so can't have a derivative there. So we've got corners. So we could have a corner on our graph, like absolute value. We could have vertical tangent line, or we could have a cusp. Those are the three ways. Or what else? So the thing about these three situations, that function is continuous. You can draw it without picking up your pencil. The one with the cusp is continuous. You can draw it without picking up your pencil. The one with the vertical tangent line is continuous. You can draw it without picking up your pencil. So those are continuous functions that are not differentiable at certain values. Or we'll go back to our theorem or to our picture. What other way could we have a function that's not differentiable if it's not continuous? So anywhere we have a discontinuity is also a place where our function is non-differentiable. So like thinking about, remember we've got the 3 discontinuities, and we've got the hole, which, okay, hole, yeah, that works, okay. Or we could have a jump, or we could have a vertical asymptote. So any of those 3 things can cause us to not be differentiable. Or we've got the corner or cusp, but that one I would call a cusp because it's curved cusp, or vertical tangent. So if we have a graph that does not have a hole, it does not have a jump, does not have a vertical asymptote, does not have a corner, does not have a cusp, and does not have anywhere it has a vertical tangent line, okay, those are nice functions. Those are nice looking functions. We've got nice smooth curves. Okay, so continuity, sometimes when you're talking about it, it's kind of in the name, right? It's continuous. You can draw it without picking up your pencil, so we don't have anything going too terribly wrong with it. Differentiability, a lot of times you can think about it as the graph being smooth. If we have a smooth graph, then that would be differentiable. So if we have continuous differentiable functions, those are nice, well-behaved graphs, nice, well-behaved functions, generally. Questions on where differentiability can fail? So that's it. We're done with chapter 2. So Friday, if you're not finished with WebAssign, come, we'll work on WebAssign. Yeah. No, it'll probably be short. The actual test probably be shorter, a little bit shorter. Yeah, good question. It's on WebAssign now. Yeah, it's on WebAssign now. I don't think I remembered to link it on the Canvas yet, but if you log into WebAssign, the practice test is there. Yeah. So Friday we'll work on WebAssign. Monday we'll go over questions from the practice test, and then next Wednesday will be test 1. Okay? One second, let me stop this.